Module 6, Fieldbus and Device Networks. The why, a classification you can actually remember. This module is where industrial networking stops being a technical upgrade and starts being a strategic shift. Up to this point, you and I have been living in a world where signals run point to point. Every device gets its own pair of wires, cabinets grow, cable trays overflow, drawings explode. That world worked, but it didn't scale. Fieldbus wasn't invented because engineers were bored. It was invented because home run wiring hit a wall. From home run wiring to bus architecture, the big industrial shift. Let me paint the old picture first, because understanding the pain explains the revolution. In the traditional control system, every transmitter, every valve, every switch had its own dedicated cable running all the way back to the control room. That's the classic home run philosophy shown in the tutorials Figure 1. One instrument, one cable, one termination point pass. Conceptually simple. Operationally, brutal. Why home run wiring became unsustainable. As plants grew, home run wiring created 4 compounding problems. Cost, copper, trays, glands, marshalling panels, terminations, all multiplied linearly with device count. Commissioning time. Every loop had to be wired, checked, tested, documented. One mistake meant hours of tracing. Diagnostics. If something failed, you knew where the signal went, but not why it failed. No device health, no internal status, just a dead loop. Interoperability limits. Vendors optimized for their own hardware. Mixing devices meant custom wiring rules, special cards, special handling. The system worked, but it was rigid, expensive, and blind. Scratch for the Fieldbus idea. One cable, many conversations. Fieldbus flips the philosophy completely. Instead of asking, open quote, how do I wire this signal? Close quote. It asks, open quote, how do I connect intelligence? Close quote. In the Fieldbus approach, shown in the tutorials Figure 2, one communication cable replaces dozens of home runs. Devices share the same medium. Data moves digitally, not as raw analog levels. Now each field deviagent node, not a passive signal source. A transmitter no longer just sends 4 to 20 milliamperes. It can also send diagnostics, status, calibration data, device health, configuration parameters. That single change transforms the entire system. Why industry accepted the risk of sharing a bus? Sharing a cable sounds risky, and early engineers were rightly skeptical. So why did Fieldbus win? Because the benefits outweighed the fear. Cost, where the numbers finally made sense. Fieldbus dramatically reduces cable quantity, tray congestion, marshalling complexity, I/O card count. One cable now carries multiple instruments, multiple data types, multiple conversations. The capital savings are obvious, but the operational savings are bigger. Commissioning, from wiring to configuration. With Fieldbus, commissioning shifts from open quote, is this wire correct, close quote, to open quote, is this device configured correctly, close quote. That's a huge mental shift. You spend less time tracing cables, ringing out loops, and more time assigning addresses, mapping parameters, verifying communication. Commissioning becomes systematic, not manual. Diagnostics, the quiet superpower. This is the part many people underestimate. Fieldbus doesn't just move process values, it moves context. Devices can report internal faults, sensor degradation, electronics temperature, communication quality, This turns maintenance from reactive to instead of open quote, the loop is dead, close quote, you get open quote, the sensor is drifting, the actuator is nearing failure, the device lost synchronization, close quote. That's a completely different maintenance philosophy. Interoperability, the long-term win. The tutorial highlights one of the biggest strategic drivers, interoperability between manufacturers. Fieldbus standards define device BE rules, data models. So devices from different vendors can coexist on the same network, at least in theory and increasingly in practice. That breaks vendor lock-in, and plants care deeply about that. The mental shift you should lock in. This episode is not really about cables. It's about where intelligence lives. Home run wiring treats intelligence as centralized. Fieldbus distributes intelligence to the field. That single shift explains why wiring shrinks, why diagnostics improve, why commissioning changes, why device networks exist at all. Once you accept that field devices are computers, not just sensors, Fieldbus stops feeling exotic and starts feeling inevitable. And now that you understand why industry moved to Fieldbus, the next question becomes natural. If everything shares a bus, how do we classify these networks so they actually make sense? That's where the bit, byte, message classification finally earns its place. Have bit versus byte versus message buses. Why? What kind of data decides the network? This episode is about classification that actually sticks, not vendor names, not protocol acronyms, but a simple engineering-first way to decide which network belongs where. Because here's the truth, most people learn late. Open quote, you don't choose a field network by popularity. You choose it by the size and meaning of the data you need to move. Close quote. That's it. Once you see that clearly, Fieldbus and Device Networks stop looking like a confusing zoo and start lining up logically. Start with the only question that matters. Before any standard, ask this. Open quote, what kind of information am I trying to move? Close quote. Is it a simple on-off, a few bytes of status and control, or structured multi-parameter process data? That answer forces the network choice. This is exactly why the tutorial classifies industrial networks into 3 families. Bit-oriented, byte-oriented, message-oriented, the way a plant actually experiences them. Bit-oriented networks, when reality is binary. Bit buses live at the very edge of automation. They deal with presence, absence, on-off, true, false, nothing more. Typical devices here are proximity switches, limit switches, push buttons, simple pneumatic actuators. These networks move bits, not values. The data answers questions like, is the sensor active? Has the switch closed? Is the actuator energized? No scaling, no diagnostics, no nuance, because none is needed. That's why these are often called sensor buses. Their job is fast, simple state detection. They prioritize speed, simplicity, deterministic behavior. Trying to move rich diagnostics here would be pointless overhead. Byte-oriented networks, when devices become smart. Now, step 1 level up. Byte-oriented networks exist because many field devices are more than binary, but not full-blown control systems. Here, devices exchange multiple parameters, status words, commands, measured values. We're talking bytes, not bits. Typical devices include motor starters, variable speed drives, barcode readers, pressure and temperature transmitters, analyzers. These networks are often called device buses. And DeviceNet is a classic example mentioned in the tutorial. Here, the networks sing structured data, moderate bandwidth, cyclic and acyclic messaging. The device isn't just saying, I exist. It's saying, here's my value, here's my status, here's my fault code. That's a completely different conversation. Message-oriented networks. When systems talk to systems, now we reach the top of the hierarchy. Message-oriented networks deal with rich, structured information, often more than 16 bytes per exchange, as the tutorial notes. These networks are designed for conting tools, operator interfaces, configuration and diagnostics, intersystem communication. Examples include Foundation Fieldbus, PROFIBUS, high-level industrial Ethernet protocols. Here, messages may contain multiple process values, timestamps, quality indicators, configuration blocks, control logic interactions. This is no longer device talking to controller. This is systems negotiating state. That's why these networks are often called Fieldbus in the strict sense. Why this classification is so powerful. Notice something important. This hierarchy is not about old versus new, cheap versus expensive, slow versus fast. It's about information density. As data becomes richer, more contextual, more meaningful, the network must become more structured, more intelligent, more disciplined. Trying to use a bit bus for message level data is madness. Trying to use a message bus for a simple limit switch is waste. Each layer exists because reality demands it. The one-line rule to remember forever. Here's the sentence that ties everything together. What kind of data you move determines what kind of network you need. Bits, sensor bus, bytes, device bus, messages, field bus. If you remember nothing else, remember that. Why this matters in real projects. This way of thinking prevents classic mistakes, over-engineering simple I/O, underestimating diagnostic needs, choosing networks based on fashion, blaming protocols for mismatched expectations. Once you classify the data first, network selection becomes obvious. And once network selection becomes obvious, integration becomes calmer, cheaper, and more reliable. Now that you understand what these networks carry, The next logical question is, how do popular standards like PROFIBUS and DeviceNet actually fit into this picture? That's where classification meets reality, and where most confusion finally clears. Task chart, PROFIBUS, DP, PA, FMS, one family, 3 very different jobs. This is where classification meets the real world. Up to now, we've been talking in principles: bit versus byte versus message, sensor versus device versus Fieldbus. PROFIBUS is the perfect case study because it didn't try to be one thing, it became a family. And each member exists because industrial reality demanded a different answer to the same question. Open quote, how much data, how fast, and under what conditions? Close quote. The tutorial lays this out clearly. PROFIBUS isn't a single protocol, but an assortment of compatible standards designed for different layers of automation than the way a plant actually uses them. PROFIBUS DP, when time matters more than detail. DP stands for Decentralized Peripherals, and that name tells you everything. PROFIBUS DP was built for fast cyclic data exchange, time-critical I/O, distributed peripherals close to the process. Think of devices like remote I/O racks, motor starters, drives, valve islands. These devices need rapid updates, predictable timing, minimal overhead. DP achieves this by using a streamlined protocol stack, focusing on cyclic data, eliminating unnecessary OSI layers. This is why PROFIBUS on factory floors. It doesn't waste bandwidth explaining itself. It just moves data fast and repeatedly. DP answers the question, open quote, did the output change and did the input respond right now? Close quote. PROFIBUS PA, when process reality and safety enter the picture. Now move from the factory floor to the process plant. Suddenly everything changes. You're dealing with long cable runs, hazardous areas, intrinsic safety, instruments that measure, not just switch, enter the phone. This is where PROFIBUS PA exists. PA is designed specifically for process instruments, bus-powered devices, intrinsically safe environments, pressure transmitters, flow meters, control valves. These devices don't need millisecond updates. They need reliability, diagnostics, safe power delivery, stable communication. PA trades speed for process suitability. It allows power and communication on the same pair, safer operation in hazardous zones, rich device diagnostics. PA answers a very different question. Open quote, is this measurement trustworthy, healthy, and safe? Close quote. FMS, when systems need to talk, not just devices. Now we reach the least talked about, but conceptually important member of the family. FMS stands for Fieldbus Message Specification. This is where PROFIBUS steps beyond I/O and into system-level messaging. FMS was designed for acyclic communication, configuration and supervision, data exchange between intelligent systems. Think PLC to PLC, controller to workstation, engineering. MS supports larger message sizes, flexible data structures, rich services, but it does so at the cost of speed, simplicity, which is why DP and PA became dominant in their niches, while FMS remained more specialized. FMS answers the question, open quote, how do complex systems exchange structured information? Close quote. Seeing the pattern, why PROFIBUS makes sense as a family. Here's the key insight I want you to lock in. PROFIBUS didn't fragment by accident. Each variant exists because the data and the environment demanded it. DP, fast, time-critical peripherals. PA, process instruments plus intrinsic safety. FMS, rich messaging between intelligent systems. Same philosophy, different priorities. The classification lens comes full circle. Now connect this back to episode 6.2. DP lives firmly in the byte-oriented device bus world. PA straddles device message optimized for process needs. FMS sits in the message-oriented /Fieldbus space. Once you look at PROFIBUS this way, the confusion disappears. You stop asking, open quote, which PROFIBUS is better, close quote, and start asking, open quote, what kind of conversation am I trying to have, close quote. That's the right question. And once you can answer it, PROFIBUS stops being 3 acronyms and becomes a coherent engineering solution.